So let's try once again. So um, we are looking at PCA. Okay. So what is the problem? So you have been given a set of training samples or data xi going from 1 to n training samples, but the problem is each of the xi belongs to RD, where D is much bigger than n. So this is called as high dimensional problem. Okay, so instead of this has issues, because if you try to learn any model with few training samples but high dimensional, your model will be very complex, so it will have overfitting issues, right? So if you are using it in a supervised learning setup. But anyway, just to be clear, this is an unsupervised learning problem. Okay, so this will be, if you want to, let us say the unsupervised most popular is k-means type of algorithm, so it is like that. But even for k-means, it is not a good idea to have high dimensional data. So instead of this, you want to transform this problem into xi bar I going from 1 to n. What is the speciality? This xi bar belongs to Rk, where k is much less than d. Okay, so you want to transform the problem into a lower dimensional problem. Okay, so how is that achieved? So we assume that because the problem is high dimensional, there must be some underlying low dimensional simplification. So we assume, so I am drawing in R3, but you can think of in higher dimensional. So there is a affine space. Okay, so we will talk about what's an affine space. So affine space is a subspace. Subspace passes through the origin, right? So 0 always lies in a subspace, and you shift that by some vector x naught. So every vector over here, if I take this vector and if I transform it, that becomes a vector right here on this. So any vector, so subspace plus some constant vector x naught gives you an affine space. This is the definition. Okay, and you have seen, like when you have Ax equal to b, solutions to this, if there are multiple solutions, lies in fine space. So I want you to go back and think about this and verify. Okay, so this much we have. So now what is the assumption again? So assumption is you have some underlying affine space where all your data is very close to that affine space, right? So you can, some data may not lie, like the one here, but some lie directly, some again may not lie. So those which don't lie, you want to project it back to this. Okay, and then of course you have an x naught, which is just a single number. If there are millions of points, just keeping a few more points for x naught is not the problem. But now you are able to project it on a lower dimensional plane. So each of these points are just 2-dimensional, right, instead of the 3-dimension that we had in the original space. Okay, so this is the idea. So suppose now our goal is to find the best affine space. Before even we do that, let us suppose that we know the affine space very well. So then how does the projection look? So we know, suppose if we know, what does it mean? We know the subspace, we know x naught, right? So how will that look? So we can say that because we know the subspace, we can find a orthonormal basis. So let us say u1 to uk is orthonormal basis for the subspace. Okay, so instead of s, if you permit me, I will change it to b. Okay, and then you can find b bar, which is an extension, which is uk plus 1 to un union b, is again orthonormal basis. Okay, this is the same discussion that we have been having earlier. Okay, now what we are trying to do is for a given vector, let's say xi, ith point, I know that in terms of this basis b bar, I can represent it as x ui I going from 1 to d, and I'm sorry, not d, k, and here I going from k plus 1 to d, right, x ui. This is if I am representing in terms of the modified basis. But now I want to look at points that lie in this affine space. So how does that look? So the idea is you are having some component which depends on I, which is I going from 1 to k, z I j. So this I am going to, you are going to, we get confused because there is I here. So let me take it to j. Okay, nothing changes, it's just a nomenclature, right? So this is j, and this x is I, xi. Okay, as you can see, each of these components depend upon I as well as j, right? So that's why I am representing it as zij. So now we are talking about points that lie in the affine space. So zij, uj plus, now these cannot depend upon this one, because I am now capturing the x0 elements. So this will be beta j, uj, j going from 1 to k plus 1 to d. So it actually goes from 1 to k as well, but that is absorbed here. Okay, so there will be, whenever you are looking at a affine point, affine projection of xi on, you will have something that depends, the k of them will depend only on I and j, both it will depend on, the rest of it will not depend. So this is constant for others. So if I want to be little more precise, so if I take some other point xk bar, that will be, I'm so sorry, I'm making this, so let me call it xs bar. Okay, so this will be zs j uj plus, the rest of it, it's going to be same, k plus 1 to d beta j uj, that will be the same. The only part that changes is here. Okay, so this is an affine representation. So now what is the thing we want to do is, we want to minimize this error. So 1 over n, I going from 1 to n, xi bar minus xi, this length, right? We want to minimize this, subject to my ui transpose uj equal to 0 and ui transpose ui equal to 1. This is of course if I is not equal to j. Okay, now when we are saying we have to find ui and uj, we have now, of course, so our problem is to find zs, js, beta js, and of course uis and ujs. Okay, uis, all the uis for all the n points. So this is the PCA formulation. I hope this is clear.